This is Auto R World.
Your car looks fine. It starts every morning. It drives to work. It passes inspection. But right now, deep inside your engine, something is happening that you cannot hear, cannot see from the outside, and that your dashboard will not warn you about until it's already done serious damage. It has nothing to do with your oil pressure, your coolant, your belts, or your brakes. It is a slow, silent suffocation. And if you own almost any car made in the last 15 years, a turbocharged 4-cylinder, a modern V6, or even some naturally aspirated engines, there is a very real probability that this problem has already started inside your engine right now, at this very moment, while you're watching this video. Today, we're going deep on one of the most misunderstood, most underestimated, and most financially devastating threats to modern engines on the road today: carbon buildup on gasoline direct injection engines. We're going to cover what it actually is, exactly why it happens and why the manufacturers knew it would, the symptoms that most drivers dismiss until it's too late, which specific engines and vehicles you need to worry about the most, what happens if you ignore it, and most importantly, what you can actually do about it right now, whether you want to prevent it, slow it down, or fix the damage that's already there. Stay with me until the end, because the information in the last few sections of this video alone could easily save you somewhere between $500 to $1,000, possibly more. Before we go any further, if you're new here, this channel is built around one mission: giving real car owners the knowledge to protect their vehicles and avoid being blindsided by expensive repairs. If that's something you want, subscribe right now and hit the bell. We publish every week, and every video is built around saving you money and stress. To truly understand this problem, we need to go back about 2 decades, to when automakers began rolling out a new fuel delivery technology that was genuinely impressive. For most of automotive history, engines used a system called port fuel injection. The fuel injector sat in the intake manifold, just upstream of the intake valve. Every time that valve opened to let the air-fuel mixture into the cylinder, a fine mist of gasoline would wash over the back of the valve on its way in. That constant fuel bath turned out to be extremely important, not just for combustion, but for cleaning. Gasoline contains detergent additives and is actually a decent solvent. Every single time fuel sprayed over that intake valve, it was cleaning off any oily residue that had collected there, cycle by cycle, mile by mile. The engine essentially cleaned itself. Then came GDI, gasoline direct injection. With direct injection, the fuel injector was relocated into the combustion chamber itself. Fuel is now sprayed directly onto the piston crown and into the cylinder under extreme pressure, sometimes upward of 2000 psi or more. This allows for much more precise fuel metering, significantly higher compression ratios, better thermal efficiency, and real, measurable gains in both power and fuel economy. Automakers loved it. Regulators loved it. It helped manufacturers hit tighter emissions and fuel economy targets without sacrificing the performance numbers customers expected. And it works. GDI technology is genuinely a step forward in many ways. But it came with one critical, unavoidable trade-off: the fuel no longer passes over the intake valves. And that changes everything. Here is where most explanations stop short. People say carbon builds up, but they rarely explain why, or where the material actually comes from. Every internal combustion engine has what's called blow-by. As the piston compresses the air-fuel mixture and combustion occurs, some of those combustion gases, along with hot oil vapor, escape past the piston rings and end up in the crankcase. This pressurizes the crankcase, and if you let that pressure build, you get oil leaks, seal failures, and efficiency losses. So manufacturers engineered a solution: the PCV system, or positive crankcase ventilation system. It routes those blow-by gases back out of the crankcase and into the intake manifold, where they get sucked into the engine and burned during combustion rather than being vented to the atmosphere. This is intentional, it is required by emissions regulations, and in principle it is a clean and efficient solution. But those crankcase vapors are not clean air. They carry oil mist, carbon particles, and combustion byproducts, and they travel directly through the intake manifold and coat the backs of the intake valves on their way in. In an old port-injected engine, this didn't matter much because every fuel injection event washed that residue right off. But in a GDI engine, nothing washes it off, ever. So it sits there, and every time the engine reaches operating temperature, that oily film bakes onto the metal. Cycle by cycle, heat cycle by heat cycle, it hardens, it builds, It accumulates into thick, rocky deposits that can eventually restrict airflow so severely that the engine begins to struggle. This is not a manufacturing defect. It is not a fluke. It is a predictable, physics-based consequence of how GDI engines are built, and some manufacturers knew about it before these engines ever left the factory floor. Let's be precise about what this buildup actually does to your engine, because this is where the real money is on the table. Intake valves are precision components that open and close thousands of times per minute. On a 4-cylinder engine running at 3,000 revolutions per minute, each intake valve opens and closes 1,500 times every single minute. The tolerances involved are incredibly tight. The valve must seal perfectly against its seat for proper compression, and airflow into the cylinder must be smooth and unrestricted for proper combustion. When carbon builds up on the back of that valve, several things start to go wrong. First, airflow is disrupted. The carbon narrows the opening, creates turbulence, and reduces the volume of air entering the cylinder. Less air means a weaker combustion event, and the engine's computer can only compensate so much before performance and efficiency begin to visibly decline. Second, the valve can fail to seat properly. Carbon deposits on the valve face or valve seat prevent the valve from closing completely, which allows compression to leak past it. You get a compression imbalance between cylinders, the engine misfires, it runs rough, and the computer throws codes. Third, and this is the one that people don't talk about enough, chunks of carbon can break loose. When large deposits break free and enter the combustion chamber, they can cause detonation, which are uncontrolled, violent combustion events that pound the pistons, destroy piston rings, and in severe cases crack pistons or score cylinder walls. This is how a carbon problem that should have cost $400 or $500 to fix turns into an engine replacement scenario at $8, $10, or $12,000. That is not a hypothetical. It happens. Now let's make this personal, because chances are, if your car has over 60,000 miles and a GDI engine, some of these symptoms might already sound familiar. Cold start misfires and rough running are often the first real symptom. In the morning, when the engine is cold, the valves are especially sensitive to restriction, and you might feel a shudder, a stumble, or an uneven idle for the first minute or two of operation. Many drivers chalk this up to just how the car runs in winter. It is not, it is a warning. A persistent rough idle is another sign. At a stoplight, your engine should sit at a smooth, steady idle, and if you feel a vibration through the steering wheel or if the RPM needle is slightly unstable and hunting up and down, that is a classic sign of uneven airflow or compression due to carbon buildup. Hesitation and stumbling under acceleration is also common. You press the gas pedal and instead of a clean, linear pull, you get a brief hesitation before the engine catches up, because the affected cylinders are not producing the same power as the clean ones. You may also notice a gradual loss of fuel economy. Not dramatic, not sudden, just a slow creeping decline over tens of thousands of miles that you can't fully explain. P0300 series misfire codes are another major flag. If your check engine light comes on showing random or cylinder-specific misfires and your spark plugs and ignition coils test fine, carbon on the intake valves moves directly to the top of the suspect list. Finally, loss of power under load, during towing, highway passing, or climbing grades. If the car feels noticeably weaker than it used to and the engine has high miles, this is another warning sign you should not ignore. If 2 or more of these symptoms apply to your vehicle right now, this issue deserves your immediate attention. Let's talk specifically about which engines carry the highest risk, because this is not equally distributed across all cars. Volkswagen and Audi TSI and TFSI engines, the 1.8T, 2.0T, and their variants, are among the most well-documented cases in the industry, with carbon buildup problems established since the early 2000s. BMW's turbocharged inline-six engines, particularly the N54 and N55 found in the 3 Series, 5 Series, and X5 models, are heavily affected, with many owners discovering severe buildup at 60,000 to 80,000 miles. Ford's EcoBoost engines, the 1.5, 1.6, 2.0, and 2.3-liter turbocharged 4 cylinders found in the Focus, Escape, Fusion, Mustang, and Edge, all use direct injection and are susceptible. GM's turbocharged 2.0T engine found in Chevrolet, Buick, and Cadillac applications is another affected platform. Hyundai and Kia's turbocharged GDI engines, the 1.6T and 2.0T found in the Sonata, Elantra, Optima, Sportage, Tucson, and many others, are also well-documented problem engines. Toyota's newer GDI engines are increasingly part of this conversation as those vehicles accumulate miles, and even some Mazda, Subaru, and Nissan direct injection applications are affected, though the severity varies. The good news is that some manufacturers have responded by adding port injection alongside direct injection, what's called dual injection or combined injection. Some newer Mazda, Toyota, Honda, GM, and Hyundai platforms use this approach, and the port injectors provide that cleaning fuel wash that GDI removed. If your vehicle has dual injection, your risk profile is significantly lower. But check your specific engine, because millions of vehicles on the road today do not have that protection. If you own a turbocharged car from the last decade, or even a naturally aspirated GDI engine, drop the year, make, and model in the comments below. And if you've already dealt with carbon buildup personally, share what it cost you, how bad the symptoms were, and whether the cleaning actually worked. Your experience could literally help someone else watching this video avoid a very expensive mistake. Prevention is always cheaper than repair. Full stop. The first step is to use top-tier certified gasoline, which contains higher concentrations of deposit-fighting detergent additives. It will not eliminate the problem on a GDI engine, but it reduces combustion chamber deposits and helps keep the overall fuel system cleaner over the long run. The second and non-negotiable step is to change your oil on schedule every time with the correct specification for your engine. Degraded oil breaks down into finer, stickier vapor particles that travel through the PCV system and deposit more aggressively on the intake valves. If you are stretching oil change intervals to save money, you are accelerating the very problem we are talking about. The third step, and the single most impactful proactive measure a GDI engine owner can take, is to install an oil catch can. A catch can is a small canister installed in line with the PCV system, between the crankcase vent and the intake manifold. It intercepts the oily blow-by vapors, separates the oil mist from the air, and collects it in a reservoir that you drain periodically. Quality catch can kits for most popular applications run between $80 and $200 installed, which is extraordinarily cheap compared to a walnut blast service and dramatically cheaper than an engine failure. Finally, using a GDI-specific intake cleaning spray preventively every 15,000 to 20,000 miles can meaningfully slow accumulation and help break down early-stage deposits before they harden completely. If the buildup is already there and your car is showing symptoms, or if it is approaching 60,000 to 80,000 miles and you want to get ahead of it, there is really only one method that properly removes hardened carbon deposits from intake valves, and that is walnut shell media blasting. A technician removes the intake manifold, which typically takes 1 to 2 hours on its own. With the manifold off, a specialized tool is threaded into each intake port and uses compressed air to propel finely crushed walnut shell media directly at the back of the intake valves at high velocity. Walnut shell is hard enough to physically abrade and remove the carbon deposits, but soft enough that it will not scratch or damage the hardened valve metal. The loosened carbon and spent media are vacuumed out thoroughly, the ports are inspected, the manifold is reinstalled, and the engine is returned to service. The results are genuinely impressive. Mechanics performing this service routinely pull out thick, black, quarter-inch deposits that look like chunks of charcoal, and after the cleaning the valve backs look close to factory new. From a driver's perspective, the change is often immediate. Smoother idle, sharper throttle response, and a return of the power and fuel economy numbers from when the car was newer. At a professional shop, expect to pay between $400 and $900 for a 4-cylinder engine and up to $1,000 to $1,200 for a 6-cylinder. Mechanically experienced owners can also purchase DIY walnut blasting kits for around $150 to $250. The general guidance from technicians who specialize in GDI engines is to perform a preventive cleaning between 60,000 and 80,000 miles, then repeat every 40,000 to 50,000 miles thereafter. This maintenance rhythm, combined with a catch can and proper oil change discipline, can keep a GDI engine running cleanly and reliably for well over 200,000 miles. Ignoring the problem until the engine is misfiring or until a carbon chunk causes internal damage can turn a $600 maintenance service into an engine replacement costing $6,000 to $12,000 or more. That math is not complicated. The driver who owned the car with that severely coated valve at the beginning of this video was not irresponsible. They changed their oil. They put gas in it. They did what most people do. They assumed that if the car was running and the dashboard was dark, everything was fine. But modern GDI engines have a vulnerability that the old maintenance rulebook does not cover, and the manufacturers, in most cases, have not been loud about warning their customers. Now you know what it is. You know why it happens. You know what to watch for. You know which engines carry the most risk. You know how to slow it down. And you know how to fix it properly if the time has come. The difference between a driver who knows this and one who doesn't, in dollars, in stress, in years of engine life, is enormous. If this video gave you something valuable today, hit the like button, subscribe if you haven't already, and leave a comment telling me what you drive and whether you've already dealt with carbon buildup. Every single comment gets read. Coming up next on this channel, we are going deep on another invisible engine killer that is quietly shortening the life of millions of turbocharged vehicles. If you drive a turbo car, you are going to want to see that one before your next road trip. See you in the next video.